In this lecture, we will be learning about the vector calculus of quadratic functions. The general way we can define a quadratic function is first, let's fix constants in the following way. We will have A, an n by n matrix, B, an n vector, and C, a scalar. A will give us the coefficients for the quadratic terms, B will give us the coefficients for the linear terms, and C gives us an intercept, or just a constant. And so we define our function f of x as x transpose ax plus b transpose x plus c. This A transpose ax, recall, is what we called a quadratic form. That represents the sum of all pairwise products of the entries of x. The matrix A gives us the coefficients of those terms. This B transpose x, recall that our vectors are always column vectors. So in this case, x is an n by 1, but B is a 1 by n. That's a 1 by 1 product. This product is what we usually call the dot product. And C is just a constant. So each one of these terms is just a constant. So this function f takes in an n vector and spits out a number, a scalar. And we want to think of this as the vector calculus analog of g of x, which is ax squared plus bx plus c, as we're used to in ordinary calculus. Now, when we think about ordinary calculus with a quadratic, the first derivative and the second derivative are nice. And so we want to define the vector calculus versions of the first and second derivatives of f. The vector calculus version of the first derivative of f is called the gradient of f. And this is something that we typically learn about in our first course in multivariable calculus. In the gradient of f, we write as del of f, and it is a vector of all of the first order partial derivatives of f. Sometimes we write the dependence on x in our notation in this way. So this is our, again, vector calculus concept of the first derivative of f. For the second derivative of f, we call it the Hessian. And the Hessian of f, usually written as del squared of f of x, del squared as in second derivative, or h of f of x for the Hessian, is this matrix here. And this matrix is the matrix of second order partial derivatives of f. So you see your first entry is the second order partial of f with respect to x1 twice. Entry 1, 2 is the second order derivative of f with respect to x1, then with respect to x2. And as we work to the right, the second order partial of f with respect to x1 with respect to xn. And you notice that the order of partial differentiation here matches the entries of the matrix. The 1, 2 entry, we have partial x1, partial x2. All the way down to the 1n entry where we have partial x1, partial xn. For the second row, we have the second order partial of f with respect to x2 and with respect to x1. The second order partial of f with respect to x2 twice, all the way down to the second order partial of f with respect to x2, with respect to xn. You notice that those partial derivatives match the entries in the matrix. So for instance, the n2 entry is that partial of f with respect to xn and with respect to x2. So this matrix is thought of as the vector calculus version of the second derivative of f. Now these are general in terms of any function f of x that's differentiable, which meaning that the first partial derivatives exist or the second order partial derivatives exist. You can define this. For the quadratic, we're going to get explicit representations of this. Also note that if these second order partials are continuous functions for I and j ranging from 1 to n, then this Hessian matrix is symmetric. Because, if you remember from your first multivariable calculus course, under this condition of the second order partials all being continuous, we can differentiate in either order. The second order partial of f with respect to xi with respect to xj is the same as the second order partial of f with respect to xj with respect to xi. So for instance, the 1-2 entry and the 2-1 entry are the same. That results in this Hessian being symmetric in the case where these second order partials are all continuous. Now, to look at what happens in the case of our quadratic function, we recall it's x transpose ax plus b transpose x plus c. We want to calculate first its gradient, and this will be a bit more natural if we rewrite these things in terms of summations. So recall that our quadratic form can be rewritten as this double sum, I equals 1 to n, sum j equals 1 to n, of aij times xi times xj. B transpose x we recognize as a dot product. So that is the sum I equals 1 to n of bi times xi, and then we have plus c. Let's think about setting this up to take the partial derivative of f with respect to xk. First, it will be a little bit easier if we rewrite this sum by taking out this xi of the inner sum. And so we write it as sum I equals 1 to n of xi times the sum j equals 1 to n of aij times xj. And then we have sum I equals 1 to n bi xi plus c. And this is the expression we will differentiate with respect to xk. So let's do the quicker terms first. So first, the derivative of this c with respect to xk is 0, because c is a constant. Then we have this term that's linear in the xi's, and we note that xk appears exactly once in this sum, specifically when I is equal to k. So when we take the derivative of that expression, so the partial derivative of the sum I equals 1 to n of b sub I x sub I with respect to xk, The only term that matters is the I equals k term. So this will be the same thing as the derivative with respect to xk of bk xk, because the derivatives of all the other terms with respect to xk are 0. And of course, this is just a constant times xk, so we just get bk. So these two pieces of f of x we've successfully differentiated with respect to xk. This term here requires a little bit more work. So let's delve into that. Our x transpose ax term we've rewritten in this way, and we're going to think of this in terms of where does xk appear and where does xk not appear. Because recall that the main idea here is to take the partial derivative of this expression with respect to xk, and this is simply a sum of these products xi and xj. And what becomes tricky is the case where you have an xk here when I equals k, and then you have the cases here where j is different than k and j is equal to k. So we can make this a little bit easier on ourselves by rewriting things in terms of terms that involve k and terms that don't. So let's rewrite that outer sum. So we have the sum I going from 1 to n of xi sum j equals 1 to n aij times xj. So we haven't changed anything, but let's now make a slight change and say we exclude the case when I is equal to k, which means we have to include that as its own separate term. So the term when I is equal to k, we're just left with an xk here, times the sum when j equals 1 to n of a kj xj. So we need to replace that instance of I with k. And so these are the terms that we will differentiate when we take the derivative with respect to xk of this quadratic form x transpose ax. So here we have the derivative with respect to xk of this first expression here. But note, because of the way we broke up the sum, that this first x sub I, that's never equal to x sub k. So the only way an x sub k appears in this expression is when it's this xj in the case where j is equal to k. So that means we can ignore terms where xk does not appear. Think about this sum here, this inner sum. If j is something different than k, there's no xk, and there's also never an xk out here. So the only time xk shows up is when this index j is equal to k. So we have to retain that outer sum, I equals 1 to n, I is different than k. And then we have xi, but that inner sum, again, the only term that contributes to the derivative with respect to xk is when j is equal to k. And so we get a ik xk. And there we have it. Now notice we're not arguing that this first sum here is equal to what's in the square brackets here. Rather, we are just omitting the terms that don't contribute to the derivative with respect to xk. So we got rid of all the terms that didn't involve xk. So all that remains here involves xk. For the next term, we have the derivative with respect to xk of this sum here. Let's bring that xk inside the sum, and we get sum j equals 1 to n akj, xk, xj. We can now take the derivative with respect to xk of this first term, and note that this xi, that's never xk. So this is a constant as far as the differentiation is concerned. So are the entries of a. And so we have a sum of constants times xk. So the derivative with respect to xk will just be the sum of these constants. So we have the sum, I goes from 1 to n, I differs from k, of xi, a, I, k. For the next term, we notice that when j equals k, you're going to get an xk squared. And the differentiation rule for that will be different than when j is something different than k. So let's just pop that term out as well. So we'll have sum j equals 1 to n, j differs from k, a, kj, xk, xj. And the term that we are popping out is the term when j is equal to k, and so we get a, kk, xk times xk, so xk squared. And we can now take the derivative here. So concentrating on this term, for the first expression, we note that this xj is always different than xk, right? J ranges from 1 to n except the case where it's equal to k. So we have xk times constant akj and xj. So the derivative of this expression with respect to xk is just the constant akj and xj. And the derivative of the sum is the sum of the derivatives, so that term becomes the sum j equals 1 to n, where j differs from k, of those constants, akj times xj. And then for the second term, we notice that we have an xk squared times a constant. We know the derivative with respect to xk of xk squared is 2xk, and so we get 2 akk xk. And we now notice something very nice about how this term relates to these two terms. Rewriting our expression here, we notice that this sum, we had sum I goes from 1 to n of a, I, k, x, I, but we were missing the kth term, the case where I was equal to k. But note, we have one of those here. Similarly, here we have the sum j goes from 1 to n of a, k, j, xj, but we're missing the term when j equals k. Also, we have one of those here. So we can now take this term and split it into two separate terms, which contribute and complete these sums, so that this becomes the sum I equals 1 to n of a, I, k times xi, plus the sum j equals 1 to n of a, kj times xj. Of course, here we have an index of summation of j. Here we have an index of summation of I. We could have rewritten either with any index of summation that we like. So why don't we take that second sum, change j over to I. I equals 1 to n a ki xi. And notice that these two are very similar. The only difference is in the order of the index, the two indices of a. Here we have a, I, k. Here we have a, k, I. So this is the entry ik of the matrix A. This is the entry ki of the matrix A. But recall that A is symmetric, which means aik equals aki, which means that these two sums are identical. And we can thus write it as twice the sum, I goes from 1 to n, of either. And it will be more convenient to choose the second, which is aki times xi. So we've seen that the partial derivative of our quadratic form, x transpose ax, with respect to xk, is twice the dot product of the kth row of A and the vector x. Now let's come back to the overall problem that we were solving. We had our quadratic function, f of x is x transpose ax plus b transpose x plus c, and we want the gradient. Of f of x. Here, we have found that the partial derivative of f of x with respect to xk is, first we have the contribution from this quadratic form, which we just saw was twice that kth row of A dot product the vector x. We saw earlier that we'll get the kth entry of B, bk. So this is our partial derivative with respect to xk. Now let's think about what the gradient of a function, of this function f, actually is. So the gradient of f of x is the vector of its first order partial derivatives, partial with respect to x1, partial f with respect to x2, all the way down to partial of f with respect to xn. We now use our derivation of the kth partial derivative of f to populate this vector. First, when k is 1, we have twice the first row of A dot x plus b1. When k is 2, we have twice the second row of A dot x plus b2. All the way down to the nth case, where we have twice the nth row of A dot x plus bn. And what we're noting is that this is actually nothing more than 2 times the matrix vector product ax plus b. And so this gives us the gradient of f. You can think of it as the vector derivative of f. And one thing to note is to come back to this expression and think about what it would look like if we were in an ordinary single variable calculus setting, saying g of x is ax squared plus bx plus c, so a general quadratic, and we wanted its derivative, g prime of x. We would say it's 2ax plus b. And what you can note is that this is quite similar. X transpose ax is the vector calculus version of a constant a times x squared. The difference is you have a matrix of constants, and your quadratic becomes this quadratic form. Your linear term is a dot product. And then you still have this intercept, this constant here. But notice the parallel. Here we had 2ax. Here we have 2ax. Here we had b. Here we have b. So we can see how this idea of the vector derivative of f, the gradient of f, for this quadratic function f mirrors the differentiation process that we learn in single variable calculus. Now that we have our gradient calculated, our next step will be the Hessian. So we have this gradient of f is 2ax plus b. And we write out our matrix vector product ax in this way so we can see what's happening, and we still have this plus b. Now what we want is the matrix of second order partial derivatives. So our Hessian is that n by n matrix that contains all of those second order partial derivatives. Our gradient here is the vector of all the first order partial derivatives of f. And so we are going to start using this gradient to calculate our Hessian. Now first note, this b is a constant. There is no appearance of any of the x terms in this b. So when we take second order partial derivatives, they come from this vector here, 2 times ax. So for instance, the first entry here, we have the partial derivative of f with respect to x1, just from the definition of the gradient. So if we want the first entry in the Hessian, it would be the partial derivative of this first order partial with respect to x1. We notice that the partial derivative of that first entry with respect to x1 is 2 times a11. The 1,2 entry of the Hessian would be the partial derivative. We have the partial derivative with respect to x1. And then we have to take the partial derivative of that with respect to x2. The only term that contributes to that would be this term here. And so we get 2 times a12. For the partial derivative of f with respect to x1, then with respect to x3, we take the partial derivative of this first term with respect to x3, and the only term that contributes to it is this a13. We get 2a13, all the way down to 2a1n. And we continue with this. That second order partial with respect to x2, and then with respect to x1, we would take the partial derivative of this second term with respect to x1, which would give us this a21. And this gives us our Hessian matrix. And we can see where this is going. This is nothing more than 2 times the matrix A. Now this also parallels what we saw here with our function of one variable. If we took its second derivative, g double prime of x would have been 2a. And notice we have something very similar here. It's the second derivative in this vector calculus sense is 2 times that constant matrix A. So this gives us really what we need to work with quadratic functions when we're doing vector calculus. It gives us the basic tools. And so to summarize, we have f of x is x transpose ax plus b transpose x plus c. Its vector first derivative, the gradient, is 2ax plus b. And its second derivative, the Hessian, is 2a. And this will be very important going forward. We will look at the basics of optimization when dealing with quadratic functions like this. And these are the main tools that we need. Now, one thing that's important to notice is that some textbooks will put a 1/2 here so that things work out a little more nicely. That you don't get the 2 showing up in the gradient or in the Hessian. It's just a matter of preference. We are going to work without the 1/2 there. But you can put that there, and it is common to see that. But again, this gives us the basics of quadratic functions, quadratic vector calculus.